Hello and welcome to today's Royal Statistical Society Journal webinar. My name is Richard Chandler. I am Professor of Statistics at University College London, and I will be the chair for today's proceedings. The presentation today is by Sujit Sahu from the University of Southampton. It's on the topic of downloadable estimates of air pollution for England and Wales and estimation of their health effects. And it's based around a paper that is published in the current issue of Series A of the Society's Journal. For those of you who like references, it's volume 181, part 2. Sujit is well known to many of us in the statistical community and in particular in the environmental sciences community for his work on spatiotemporal modelling. He is a professor of statistics at the University of Southampton, where he has been for some time. Over to you, Sujit.
This paper is sort of this work is based on my talk today is based on two papers, one by Mukhopadhyay and myself. He was a postdoc who worked on this EPSSC funded project. And my second part of my talk will be based on a paper with Duncan Lee, Sabyasachi Mukhopadhyay, Alistair Ashworth, and myself that has been published in Biostatistics. So the estimation of the health effects part is in the second paper, and the first paper will talk about downloadable estimates of air pollution. And all these research has been funded by the EPSAC, by an EPSAC grant, which was jointly given to University of Southampton and University of Glasgow. And we also had collaboration from the Meta office as well. Pollution is still a problem today, so this is a news clipping. This slide is a news clipping from BBC News. Air pollution, forecasters hope for cleaner air on Friday. This particular episode was pollution was blown away from the Saharan dust, and then forecasters were, forecasting that the dust storm will clear by Friday. So, and there are other headlines like London kids on high air pollution, our eyes start stinging. That's BBC News in January 2017, and so on. So we wanted to, so air pollution is still a problem, and so we want to see what's air pollution like in England and Wales. So we were looking at this automatic urban and rural network. So what you see in front of you is a map of 346 local and unitary authorities in England and Wales. So these are the boundaries, and then 144 AURN monitoring locations are denoted as blue stars and red triangles. So you can see 144 sites are mainly located in the cities and some in rural areas. So what's the statistical modeling challenge is, how do we estimate air pollution at any new point or local or any new point like a particular location here or a local authority like any of these boundaries. So, and how do we relate health outcome data and pollution? So health outcome data may be available for, or aggregated health outcome data may be available for these local and unitary authorities. So next is UK air pollution data. So we have monitoring data that can be downloaded from the website hosted by DEFRA, Department for Environment, Food and Rural Affairs. You can see data are very sparse with a lot of missing data. What this table shows, like we have annual number of air pollution observations for each of 5 years from 2007 to 2011. And we have collected data for four most important pollutants: NO2, O3, PM10 and PM2.5. You can see there are about 31 to 33,000 NO2 data because that's most vigorously monitored. O3 about 20,000, coming up to 20,000, and PM10 is low. Those are like dust, particulate matter, and they're about 17,000 and about 17,000. And what you see here is like the regulations for PM2.5 came from an EU directive, in 2008. So that's why I commented what will happen after Britain leaves EU. So hope the monitoring continues. So these 144 sites were classified into three types: rural, urban, and road and curb sites. And to show you how these data look like, how do the data look like, we have side-by-side box plots for each of the four pollutants, for box plots classified by the site types: rural, urban, and road and curb site. So it is clear that NO2 pollution is higher in the in the road and curb sites, but the converse is true, like O3 is higher in the rural areas and it's lower in the road and curb site areas. So that's because to form O3 you need NO2, and sort of O3 sort of eats up NO2, and so there is negative correlation between them. And for the two dust particles like particulate matter 10 and particulate matter 2.5, there is a little bit of a gradient for the road and curb sites, but normally the levels are similar. So what we want to do in this work is we want to model daily levels of four major pollutants for the period 2007 to 2011. So we want to build up a process-based suitable spatiotemporal model that can handle highly variable and sparse air pollution data, is more accurate than recently developed methods, is based on a spatiotemporal process which allows us to interpolate at any unobserved point location, which in turn lets us aggregate pollution levels in both space and time. In our model, we use a covariate, the output from a computer simulation model, AQM, air quality unified model, interpolated on a 1 kilometer grid, which is a very fine grid, and this was part of the work done by the meta. So our models are general spatiotemporal autoregressive models. The basic modeling setup is well documented in books by Gracie and Weichel, Banerjee, Kalman, and Gelfand on spatial and spatiotemporal modeling books. So three equations are there, like you have ZST is mu ST plus epsilon ST. So this ZST is the square root of observed data at site S and time t. And so then square root, so the first equation is square root to observed data equal to true value plus error, and the errors are epsilon st is the white noise, like independent normal 0 sigma square epsilon errors, and these are in spatial statistics called nugget effect, or which accounts for measurement error. And the excess t prime beta, so that's the regression part. I'm going to say more about that. And eta st is a space-time interaction term modeled by an autoregressive Gaussian process model. So first, briefly, what is the regression part? We allow site-wise regression lines for three site types, with SIT being the AQM value. We assume this model equation. So basically, you have a different slope and different intercept for different site types within our study region. So that's why I said three different regression lines are obtained, one each for rural, urban, and road and curb site. So in doing that, the model is fitted separately for each of the four pollutants. So modeling the space-time interaction term, we use an extended space-time model based on Gaussian predictive process. We have added further flexibility into the model by improving non-node selection process in that GPP method. The extension allows us to have more nodes in the densely populated areas, leading to better estimation in those neighborhoods. So we omit the details because that will take much longer to explain, but all models are implemented by extending the R package SP timer, publicly available from CRAN. So I show you some results. So each of these tables are for one pollutant. So the first table is for NO2, the second table is for O3. What you see here is we use about 60% data to train the model and 40% to validate. So you see fitting N is 92,000, validation N is 67,000, and in blue the SD is about 37. And then we calculated the root mean square predictive error, the mean absolute predictive error, bias, coverage, and R square. And you can see our best model reduces the overall standard deviation to about half, like from 37 to 17.65, and with a high R square of 0.89. For O3, we see similar performance. The overall SD, like 22.23, reduces to 10.17. So this is what we said, that our modeling roughly halves the error variability in out of sample validation. Similar pictures we see for PM10 and PM2.5. The overall SD for 11.98 has been reduced to 5.48, and then for PM2.5 it is about 10 reduced to 4.3. So we also wanted to compare with work from other people, but that is something difficult to compare our error rates with those from other articles, as there is non-modeling UK data for a 5-year period. What the closest we found is a paper by Pirani et al. In 2014, who modeled daily PM10 data for London for 728 days during 2002 and 2003. So if we use data from London only, using 24 fitting sites and 5 validation sites with London, then we see our result, our root mean square predictive error is 3.81 compared to theirs 4.75, but that's for their data, so strictly it is not comparable, but that's the closest we got. So now we come to talk about the aggregating to local authority areas. That's a difficult integral. How do you get estimate for a local authority for a polygon inside our study region? That's a difficult integral. We can write it as written there on equation 1. We estimate that integral by block average of nk grid corners within each local authority. So you see the equation there, and we use so that's summed up in this slide here. We have a map of, you see this map of 346 LUAs in England and Wales, and it is covered by 151,000 grid dots, which are 1 kilometer square grid. So we average air pollution in an LUA as the block average of the pollution levels in the green dots falling within each LUA. So our best Bayesian model is used to interpolate model the air pollution at each of these green dots. That's the time consuming, that takes a lot of computing time, but we produce air pollution estimate at any LUA or at any higher level geography that we like to. So one example of that is this local authority-wise annual prediction plot for NO2 and their standard deviations on the right-hand panel. You can see NO2 levels are higher in the cities like London and Birmingham, Manchester, or you can read those cities out. And those are significant air pollution because the annual standard is 40, annual limit value is 40, and it is exceeded in most cities in 2011. And what's our contribution here is the map on the right. We get uncertainty estimates. This is, we haven't seen uncertainty estimates like local authority-wise uncertainty estimates. So we do that. And you can see one thing from that map on the right, that we didn't have any monitoring site in Cornwall, and so the uncertainty for Cornwall on the bottom left-hand corner is a lot higher. We have similar maps for the other three pollutants. So we have O3, as told before, the O3 pollution will be higher in the rural areas of Wales and north of England, and it's much less in central London and the city areas. And we got the standard deviations as well. For PM10 and PM2.5, which is the next slide, we see similar estimates. And there, remember the gradient between the rural and urban sites is not much, but still we see sort of pollution levels are higher in the southeast and in the, that's for PM2.5. So I'm going to talk a little bit about estimating the health effects, which is based on our joint work with Duncan Lee and co-authors. So, so, so what we would like to model is YKT, which denotes the number of hospitalization in the kth local authority, AK in the tth month. So K equal to 1 to 323 local authorities in England. We looked at the effects in England only, and our T is from 1 to 60 for 5 years. So this YKT follows Poisson, EKT, RKT, that's a standard disease mapping model, and EKT is a directly standardized hospitalization by age and sex, which counts nationally. And we model the relative risk, RKT, as an overall intercept, plus effect due to pollution, that V hat KT, which came from our model, and then two confounders, average job seekers allowance in that local authority and average house price. So these are confounders for respiratory diseases, and we took a psi KT, which is a space-time random effect, for which we had elaborate models. So the results from the health outcome model fitted to, we see for NO2, the relative risk is estimated as 1.028 with a 95% interval of 1.021 and 1.033. This relative risk is for one SD increase, like standard deviation is 16.07 increase in pollution. So an estimated 2.8% increased risk of hospitalization due to 1 SD increase in exposure NO2. Similar interpretation for the other effects, you see that O3 and PM2.5 are not significantly affecting hospitalization according to our model. So this implies that 17,000 extra hospital admissions per year, as there are around 613,000 admissions per year in England. This implies a potential annual spending of about £5 million, assuming a week stay on average for each patient in the hospital. So I'll quickly come to conclusions. So we have developed pollutant-specific models which work well for all four important pollutants, PM10, PM2.5, O3, and NO2. Our models fill up the sparsity of the observed air quality data by integrating output from the AQ arm, which are available over a fine grain. We are able to estimate pollution levels along with their uncertainties at any desired level of administrative geography, because we can just block average up, and we are able to measure long-term exposure since we have modeled daily data for a 5-year period for all four pollutants. We are not aware of any similar study offering high-quality air pollution estimates along with their individual error bars. So that's like we estimate air pollution at a local authority level, we have error bars for that, and so on. So all these pollution data are available for doing further science, basically exposure estimates and their uncertainties from our best model for all four pollutants at both daily and annual timescales for the 5 years 2007 to 2011 at the 151,000 1-kilometer grid points, and also for all the local authorities in England and Wales are available online. And this total size is about 64 gigabyte. This is from my own website, and there is a link to that on air pollution estimates. So thus we provide the most accurate empirically verified air pollution estimates at 1-kilometer grid in England and Wales for the 5 years. So this is where I say that we have provided the data, so hope colleagues can do science. So what you can do with these, so that's why I have a couple of slides. So future data uses, possibilities are really endless. So government and regulatory bodies can use the data to evaluate post-hoc compliance to air pollution standards in even unmonitored areas all over England and Wales. Compliance can be evaluated at any socio-economic, political, geographic scale. Sorry about the long term, but like postcode, local authority area, LSOA, electoral wards, etc. And researchers from both academic and government agencies, such as the Public Health England, can link air pollution to a range of health outcome data. And for example, colleagues in UCL are associating air pollution levels with the Millennium Cohort data on children's mental health. And future work, improve the models by further methodological development, easy multivariate models for the cohort 4 pollutants, obtain similar exposure estimates for 2012 to 2017, possibly using new and improved models, develop online tools or what we call apps to deliver data sets on the fly. So suppose any user wants only data for London, certain boroughs of London, can they get it for any scale they want, any time scale they want. So user defined geographies and what's the time domains like monthly and quarterly, etc. And evaluate health impact using rigorous epidemiological studies. There may be many health outcome or health endpoints that that we need to look at and see if they correlate with the air pollution levels that we publish. So with that, my email is there, sk.s.k.sahu@southampton.ac.uk. So I'll be very happy to receive your queries regarding this. So thank you very much.
Okay, thank you very much indeed, Sujit, for a very interesting presentation describing a lot of hard work by both the authors and the computer, I think. We're going to hear now from Professor Jonathan Rougier, better known to many of us as Jonty, who is at the University of Bristol and again is very well known within the environmental science community, in particular for his work on uncertainty and the use of computer simulators to study space-time processes.
Thanks, Richard, and thank you also, Sujit, for a fascinating talk and two really inspirational papers. I focused on the first of the papers that you discussed, in particular the issue of the construction of the model. Before I say something about that, let me just give you some initial thoughts on this paper. Exactly as Richard said, there is a huge amount of work in this paper that it's not always obvious, I think, in the slide presentation, unless you've had to try and do this kind of stuff yourself. And then you really know how challenging it is to synthesize data sets, especially spatial temporal data sets from different repositories in a single inference. And if you look at the underlying paper, there's much more detail about the many different repositories that were consulted here in order to do this analysis. So it is a very inspiring piece of work and a huge amount of effort. The availability of all this data online is another very strong feature, and undoubtedly that will become much used, exactly as you say, through people in agencies and departments, and also people studying health economics. I also liked in the model the acute treatment of non-stationarity. You didn't talk about it in your slides, but there's a very nice treatment of non-stationarity, very adaptive, both to the data that you're modeling and to the resources that you have available. So people who find themselves wrestling with spatial temporal problems that are obviously non-stationary, this model is very attractive for that purpose. The questions I want to look at briefly are the questions about validation and justification. The outer sample performance of your Sujit's work is really excellent, both in terms of its absolute reduction in variability, but also in terms of comparison to other algorithms. So that's very impressive, and that's definitely one reason for using it. The other reason obviously has to go into the practicalities much more. The practicalities, they come in two strands, really. There's the question of whether it's possible for other people to implement the model on their computers. And that's really an issue about how easy it is to code up the model, how easy it is to code up the inference, and to extract the summary measures. And that's obviously not to be sniffed at. Those of us who do this kind of thing know the danger of coding errors and the attraction of simple frameworks for doing inference. And the point that I would like to make about this particular paper is that Sujit's implementation of the paper was a full-scale MCMC. That's a Markov chain Monte Carlo, not just over the parameters that control the process, but over the process itself. The process itself is part of the MCMC. And the point I wanted to make about this particular application is that needn't be the case. this application is sufficiently simple that it actually breaks down into a framework which we call the Kalman filter. And in the Kalman filter, if you put aside the issue of the hyperparameters for the moment, what you find is that you have a linear relationship between the state vector, which in this case is a whole bunch of knots, e to star t, and its value at a previous time period. So this is the simple Markov process. And you have a linear relationship between the observations, which are the zt's here, and the state vector given in the first equation there. This is basically a bog standard Kalman filter, and the only interesting feature about it, of course, is that the coefficient vectors, which are known, that is the rho and the f sub t and the mu t, they are time varying, which doesn't cause any difficulties with a Kalman filter at all. It's just an interesting aside, but those are known quantities. So this is basically a Kalman filter, and we know some things about Kalman filters which weren't exploited in Sujit's analysis, but I think could be very useful. So first of all, there was a section in the paper about missing values. Missing values are not a problem for a Kalman filter. They get integrated over automatically, so there's no difficulty with missing values. Sujit, you implied the condition that the initial value of the state vector was strictly 0. That can be lifted. The state vector in this case has a stationary distribution, and you can sample eta naught from the stationary distribution instead of imposing a hard boundary, which is unattractive for all sorts of reasons, unless you have a long spin-up period, which is computationally expensive. There's a simple closed form expression for the likelihood of the hyperparameters. This is an expression that's computed iteratively, basically just by taking the sum of logs. It's a very simple thing to do in practice. It's closed form, so it evaluates on a computer, in microseconds, effectively. And there's also a simple sampling algorithm for reconstructing the state vector on the basis of the observations and the parameters. So these are all special features of the Kalman filter, which do not exist in general for state space spatial temporal models, but do exist in the case of the model that you've analyzed here. So it's interesting that these are all opportunities that you have essentially to exploit the special structure of your model that it doesn't look as though you used in practice. So were you to use the Kalman filter approach, and this is not a large Kalman filter, just judging by the dimensions that you gave, then the appropriate procedure is to MCMC over the parameter space only, rather than the product of the parameter space and the state vector over all times, using the closed form expressions for the likelihood function and the prior, basically to draw samples from the distribution of the parameters given the observations. And that's a simple process in this case using MCMC because the dimension is small. It's only as small as the number of hyperparameters. And then you can use the closed form expression or the smoothing algorithm for the state vector to generate samples of eta star, reconstruct the full latent process using the observation equation, and then extract summary measures. That looks like a much more efficient approach than doing full MCMC on the product of the parameters and all the state vectors over all time points simultaneously. So the question that I'd like to ask is for you to reflect on whether that actually is a possibility for your particular calculation, and then to discuss why you didn't go down that route in practice. Thank you.
So thank you, Jonty, for doing a very nice discussion. So I just prepare one slide, so reply to the discussion by Jonty. So thank you. We gladly welcome the suggestion of using the alternative computation technique based on the marginal likelihood, L theta, and Kalman filtering. And I must say that SPBase, the software package SPBase, does that. It works on the marginal likelihood. In fact, researchers are free to use their preferred computation techniques, and software is in last, and I'm sure there will be people attempting this. So, but what in our case, note that L theta will be a function of sigma square eta plus sigma square epsilon. That's for a simple model where your FT was identity. So this implies the loss of conjugacy when sampling from the full conditional distributions of these variance components. So when I want to sample from sigma square eta or sigma square epsilon, they will come in the likelihood, in the marginal likelihood as a sum. So that's not a problem, but you can, in that non-conjugate case, we need a Metropolis Hastings scheme, which we need to tune the acceptance rates for optimal performance. This will require additional input from the user. So you need to tune to have about 30 to 40% optimal acceptance rate. And so instead, what we did, our sampling-based approach for the eaters was like the spatial random effects, is our preferred method, and we found that this is readily available in current package SP timer, so we use those. So in summary, basically, we agree that more efficient computation techniques can be implemented, and people, I'm sure, will try Kalman filtering and inline and stand. But because you say the convergence was so quick, we didn't face any problem in sampling the whole thing, which was readily available from the current package. So that's why I wanted to say that. And thank you. And maybe this will be future work. We all want to do better model and do for the other years as well. So that may be something to look at.
So I'm going to read out the email that we received. In your introduction, you rue the sparsity of monitoring sites, but I would hypothesize this to be expected for an island nation, substantially isolated from our European neighbours. Are there comparable studies for Ireland? There, the population density and mean disposable incomes are significantly lower than in England and Wales. So Sujit, I wonder if you'd care to respond to that question.
Yeah, so that I admit that I haven't looked at monitoring from for Ireland at all, and it will be an interesting study. There are, I think, a couple of monitoring sites like which are in Northern Ireland, but we haven't looked at monitoring sites from Ireland at all that we should look at in any future study.
Okay, thank you. There is another question that in the same email that says, for the two gases in table 2 of your data description, the means are close to the medians, but much less than the maxima. Mike writes, this militates against the assumption of the normal distribution, which appears in much of your subsequent analysis, but perhaps is justified because this is concerned with variances rather than averages. I wonder if you care to comment on that one.
Okay, so I'll repeat the question. The question is basically from table 2 of our paper, which shows the means and medians are close of the air pollution. Means and medians are close, but the maximums were far away from the means and medians. So that's how can we justify normality? That is indeed a very valid question. And for that, we model everything on the square root scale, which helps sort of bring back the tails, the large tails towards the center. And also we have looked at like the effects of the roadsides affect very high values. So some of the covariates do affect the these large values, and we model on the square root scale. And the summaries that we presented in the paper are on the original scale. So they look a lot bigger, but on the square root scale, the values are a lot, lot more central, lot more well set. So, and it is common that people use square root scale to model air pollution. And of course, it will be nice to use more realistic statistical models, but that will be future work, and that will require a lot more computation to do this.
Okay, thank you very much. Looking at the conversation pane, I think, in fact, we can stay in Southampton for the next one because we have the question from the floor.
Yeah.
So
this is Harry.
The question seems to be: does the metropolis need to be used in particular for the non-conjugate sampling, or can any sampler be used? I think this is related to the discussion with Jonty about the computational methodology for doing the inference.
Yes, that's correct. So it is how we said that when we use the marginal likelihood, we lose the conjugacy. And the proper thing will be to do the metropolis Hastings, and it's the you can use any methods in Metropolis Hastings so that it still remains a Markov chain. You cannot just use any sampling scheme. It must be a version of Metropolis Hastings. And because there is no conjugate sampling, so we have to use a proposal and then sort of use Metropolis Hastings to accept or reject that proposal. And that once you do that, then Metropolis Hastings, the acceptance rates should be monitored and they should be tuned so that the proposal distribution should be tuned to have acceptance rates roughly between 30 to 40% for one-dimensional sampling update. So yeah, that's a nice question. And so that's for every time you run the MCMC, you have to sort of tune that proposal distribution.
Sujit, can I just clarify your Metropolis step? You seem to be using a random walk proposal for a 1D parameter. Did you not think about using a slice sampler because they're almost invariably far more efficient and don't require any tuning?
Yeah, I mean, you can use that. That's an alternative as well. So, but the space that you are looking at, these various components, because you see it gets added up, this sigma square epsilon and sigma square eta, they just get added up. So there will be problems in the sampler, no matter what you do, I think. You can use slice sampler, and that should be acceptable.
Okay, thank you. I can see that somebody is currently typing a message, but they've been doing that for a while, so it's obviously a long one. So to give them time to finish, I wonder if I've got a more kind of applied question of my own, if I may.
Okay.
Looking at the map of the monitoring locations, I wonder if there is an issue of preferential sampling with these data, in the sense that it seems very, very clear from the monitoring locations that air pollution is a big concern in London, and maybe less so in other urban areas. Now, I know that you've got covariates in your model that are intended to capture the difference between urban, rural, and road and curbside locations, but I do wonder whether the sampling needs to be thought about quite carefully, particularly if you're going to make claims about health impacts and economic costs of air pollution.
Okay, so Richard's question is about the map is on what was the past map, right? The map of the monitoring sites. Yeah?
Yeah.
And so basically Richard's question is about, is there a preferential sampling for the cities, road and curb sites and the city sites? Yes, I think those are part of the network design. When the networks are designed, they wanted to monitor where people live and work. So that's why you see that. And I think preferential sampling would be an issue here. Gavin Shaddick and co-authors have done some work on preferential sampling, and we have a paper with Alan Gelfand as well on preferential sampling. You can, in our Bayesian modeling scenario, you can use the preferential the location of the sites as random as well, and do a, use that information in the model. So, but that will be more elaborate model that we will be looking at. But saying that, I think the predictive maps and everything that we have drawn, we have sort of adjusted for that in the sense that in our model, the sites are explicitly spelled out, whether they are roadside or the curbside, roadside or urban or the rural. And also the predictive maps were based on 1 kilometer, sort of 1 kilometer grid of predictive sites. And in those predictive sites, we knew which ones were roadside using open map, open map data. The details are in the paper. So we used quite a lot of site characteristics in the predictive maps already. And of course, the further information we add, we will have better predictive maps. But so this work has gone as far as we could take it.
Okay, thank you very much. While you were responding to that question, the previous one was completed. So this one is from Kevin McConway.
Yeah.
You may be able to see it yourself, but I will read it out.
Shall I read it for the audience here?
Okay.
So I have so this is from Kevin McConway. So I have a vague question. The NO2 measures are daily maxima, and the ozone measurements are daily maxima of running means. Does this cause an issue when scaling it up to the local authorities? No, we use the statistic explicitly in our paper. The NO2s are not the daily maxima. They are the 24-hour mean or something. NO2s are 24-hour mean in our paper. And O3 was 24-hour mean as well, I think. I mean, if it's the maxima that matter for health effects and the local authority figure is a mean of the maxima, is that the right measure for considering health impact? So what I say to that is we use the daily statistic, which is in the EU directive. So we haven't used anything else. So our daily statistics are aligned to the EU directives, and that's how we model it. And of course, you can use other sort of more relevant statistics, like some of our earlier modeling work was on annual fourth highest, 3-year average of annual fourth highest statistics, but that's, we are not going there yet. Thank you for the question anyway.
Okay, thank you. I saw that your co-author started to type something while you were responding there.
Okay.
I wonder if he wants to contribute something.
Actually, to answer, I just want to answer one question by I think somebody asked that what if we use the sample size samplers or something else? Actually, I did experimented with all these. Okay, now in our model, all the parameters are nice heroes except for phi. This is the deadly villain. So the problem is that I have studied some of the papers, and most people have said that estimating the sigmas and phi at the same time consistently is not possible. So most people, even Professor Sahu in his previous paper, what they have suggested that to choose the value of phi empirically and then simulate rest of the parameters. Now, what if we choose phi empirically, rest of the parameters does not create any problem at all. So be it metropolis, be it anything else, okay. But if phi is actually simulated, then it becomes a very big problem. So then metropolis testing sometimes failed. I mean, it fails really miserably. And then I have not checked whether size samplers or other techniques, or I was getting some suggestions that R-in-law or R-stan or many other possibilities can be done. But my main point is that what I want to emphasize, that estimating the parameter phi itself is a problem. So good mixing of the MCMC chain may not always indicate that the optimal value of phi have reached. So one definite way out could be to choose phi empirically by consulting a set of possible values. And once we do that, for other parameters, these sampling techniques doesn't make much difference, at least what I have found. Even what Professor Sahu was mentioning, that if I marginalize the model, estimation will be really a problem, because what I did, I think a few days ago, what I did, that I simulated an artificial model where I have all the parameters known to me. Okay. Now, when I estimate sigma square phi, sigma square epsilon, and sigma square eta, I find that for the best model, when the estimations are really good, they really add up to the variance of the whole data. So even if I choose sigma square phi and sigma square epsilon to be very small, but I make other parameters to be like that, the data is really sparse, these two parameters always add up to capture the data variability. So like other theoretical authors, they have emphasized that estimating these parameters are not straightforward. So, I mean, whatever we are getting, end of the day, we should be happy with the final prediction. That's what I have found by experimentation. Okay.
Thank you very much indeed for that. That's very helpful clarification.
And the other question that NO2 measures, actually we have used, I think, this 24-hour average for nitrogen dioxide, but for ozone it would be maxima of 8-hour running mean. Okay. So, but then I will say the results will not be much different, and particularly why we have not tried with something else, because these summary statistics are actually used by Met Office while reporting the pollution. So these are standard. So anyone who is doing anything related to pollution and linking to this health effect, at least in the Met Office, will be doing that. So that's why we have taken this to be standard, because even EU specifies their guidelines like 40. This concentration of NO2 40, this is also specified in the same measures. That's why we have used them.
Thank you very much indeed. That's I think the fact that this is the standard way of doing it is as good a reason as any to do it, I guess. I'm sorry to cut you off there, but we are at the end of the allocated time for the webinar. So I will finish by thanking, first of all, Sujit for a very interesting presentation, John T for his time in thinking about that and coming up with some thought-provoking discussion. Thank you to all of the participants. I hope you've got something out of it, and thank you all for joining us.